In this video, we'll talk about initial value problems for second-order differential equations. So we already know how to think about general solutions versus initial value problems for first-order equations. Now we're going to step into what that looks like for second-order equations. The main idea to think about here is, again, I want to figure out what I need to do to fully specify a solution. First-order equations, there was one constant c, so picking one initial value for the function let us determine what c was to get our solution. For second-order equation, there's going to be two constants, and so I'm going to need two initial values to determine what the constants should be. In general, they are given in the form of the function and its derivative at a single point in time, but there are some methods you might see in other classes that will involve having the function defined at two different points being the way these are specified. The brief example, see what this might look like. So if y double prime is t squared for y of 0 equals 1, y from 0 equals 2, this is a simple enough equation where it just depends on t on the right that I can just directly integrate this twice. So if y double prime is t squared, that means that y prime is going to be t cubed over 3 plus c. And now I have to integrate this expression. To integrate this, I will then get that y is t to the fourth now over 12 plus ct plus d. Note that I also integrated this c here to get ct. That's how that's going to work out. And now I can find what the constants need to be to meet the initial conditions. So for this first one, y of 0 equals 1, if I plug in 0, I get that y of 0 should be 1, and that is 0 plus 0 plus d, so d is 1. Y prime of 0 equals 2, I can plug into y prime up here. Y prime of 0 being 2 is 0 plus c, so that c is 2. Therefore, my solution is going to be y of t is t to the fourth over 12 plus 2t plus 1. The important thing being here, I integrate twice, I have two constants, and I need two initial condition values in order to specify what those constants must be. Now, in more general cases, you won't have these constants from integration, but from other methods of solving, we'll have two constants. The important thing you should always have in mind is because it's a second order equation, I should always have two constants. And so you're always looking for how can I get those two constants, and then what are they going to have to be to make all of this work. So because these equations are linear, we know that if I get two solutions, y1 and y2, then the linear combination c1, y1 plus c2, y2 is also a solution. We'll go into more detail on this later. We can just say at the outset, let's assume that that's the case. We want to know, is that enough to meet every initial condition? Because I have two constants. So ideally, with two constants, that's enough to do things. Because I'm going to have two initial conditions, say y at t0 equals a, and y prime at t0 equals b, and I want to know if my two constants here are good enough to meet all initial conditions. Let's see what happens. If I set y equal to c1 y1 plus c2 y2, then y prime is just c1 y1 prime plus c2 y2 prime. And now I can plug in t0 and try to match them to a and b. So a is y of t0 is c1 y1 at t0 plus c2 y2 at t0, and b is c1 y1 prime at t0 plus c2 y2 prime at t0. Now my goal is to solve for c1 and c2 here. So to do that, I'm going to multiply the first equation by y1 prime at t0. My goal is to use elimination here to solve this out. And the second equation, I will multiply by y1 at t0, because then when I subtract these two terms are going to cancel, because I'll see c1 y1 t0 y1 prime, c1 y1 prime y1. So those will cancel out, leaving me with a y1 prime at t0 minus b y1 at t0 equals c2 times y1 prime at t0 y2 at t0 minus y1 at t0 y2 prime at t0. And then I can solve for c2. So c2 is going to be this expression here, and then I can solve for c1 by back solving things out. But there's one issue. This works so long as the denominator is not 0. So as long as this part is not 0, then we're good. I can solve for c1 and c2, and everything's great. So that condition here actually ends up being really important. This condition is what tells us, are these two solutions that I found, this y1 and 2, are they different enough so that I can meet initial conditions? And it's so important that that's what we use to actually determine what's going on with these equations. So if y1 and y2 are two solutions to a second order linear equation, then I can use that to meet any initial condition that I want, provided this difference here is not 0. This was the denominator. It's negative, but it works the same way, so it can't be 0. If this fact is true, this gives us the ability to call this a general solution. So if this is true, then c1y1 plus c2y2 is the general solution to that differential equation. Because I can use it for every initial condition, it satisfies the idea of being a general solution. As a side note here, there is another theorem in this area called Obel's theorem, which basically says that the function that I'll call w of t, which is y1 of t, y2 prime of t, minus y1 prime of t, y2 of t. Basically, it's the same thing as above, but instead of plugging in t0, I just leave it as a function of t. Obel's theorem says this function is either always 0 or never 0. Either it is the 0 function no matter what t you plug in, you get 0 no matter what, or this function never touches 0. And so that means to check the condition above for if you have a general solution, all you have to do is check any one convenient point. And then that will let you know that these are in fact different, and you get a general solution out of these two separate solutions. So that's how we get general solutions for these equations, and how we can tie that into being able to solve initial value problems. Once we have a general solution, we can then just go ahead, set the two values that we want, and then figure out what the constants need to be to meet those initial conditions to solve the desired initial value problem.